The principle of analog to digital conversion is easily understood by using the analogy of a movie camera. The camera takes about 30 pictures of a moving object every second. Each picture represents a static event. Yet, when the pictures are played back in the same sequence and same rate, we get the perception of motion. Now let's consider an analog signal. The analog to digital converter measures the signal voltage at discrete points of time. Each measurement is called a sample. The number of samples collected per second is the sampling frequency. In this example, we have collected 20 samples in 1 second. Hence, the sampling rate is 20 Hz. The sampling interval is the time between successive samples, and it is obtained as the reciprocal of sampling frequency. In this example, it is 0.05 seconds or 50 milliseconds. The digitized signal is the array of voltage values stored in this manner. This record is used for signal processing, measurements, and display purposes. A simple method to display the digitized signals is by making a plot of sample data using straight lines. The reconstructed signal in this manner is very similar to the analog signal. The resemblance to analog signal can be improved by using more sophisticated line drawing algorithms. The similarity between analog and digitized signal depends on the sampling frequency. It is the same potential digitized after reducing the sampling rate by 50%. Let us compare this digitized signal to the analog signal, which is now shown in blue color. Note that the digitized signal appears smoother and does not have many peaks. Its rise time is much higher and the amplitude is lower. This waveform distortion is called aliasing. It occurs in the portion of the signal where it changes rapidly, that is, where it has high frequency components. When the signal changes slowly, as seen in the terminal phase of the potential, the analog and digitized potentials are quite similar. Thus, the sampling frequency for good quality digitized record must depend upon the high frequency signals in the potential. The Nyquist theorem states that the sampling frequency must be more than 2 times the highest frequency in the signal. As example, in the needle EMG recordings, the high frequency setting is at 10 kHz. Hence, the sampling rate should be at least 20 kHz. Modern systems often use a sampling frequency of 40 kHz or higher. While the sampling frequency defines the resolution of signal in time, the number of bits in the A to D converter define the resolution in voltage. Modern systems use 16 to 24-bit A to D converter and offer sufficient resolution in the range of nanovolts.